Welcome to solverfy.
Okay, so during chapter 22, problem 31. So we're considering the thick spherical shell of problem 29, which we have here, where the spherical shell was a non-conductor, so it had charge distributed uniformly. But now we want to imagine this spherical shell as a conductor. So it still carries a total charge of Q, and at its center we have a point charge, little q. So now we want to figure out what the total charge is found on A, the inner surface of the shell. So the inner surface. So for a conductor, we know that the charges are all on the surfaces. So that means the total charge of the conductor is given as Q inner plus Q outer, because those are the only two places they can accumulate charge. So now we want to create a Gaussian surface that just barely encloses the inner surface. So since the electric field inside of the conductor must be zero, we know that the enclosed charge of our Gaussian surface here is Q inner plus little q. We also know that at this point, there's got to be no electric field. Why is there no electric field there? Because that's inside of a conductor. If we draw our Gaussian surface out here, that is inside of the conductor, and E must be zero inside of the conductor. The only way that can happen is if the total enclosed charge is zero. So immediately we can see that Q inner must be negative little q. It's the only way for it to be zero electric field inside the conductor. Part B says, what is the total charge found on the outer surface of the shell? Well, Q outer is just Q minus Q inner, or Q plus Q. Awesome. Easy enough. Part C. Part C wants us to determine the electric field for R less than R1 greater than 0. So if we draw a Gaussian surface here, we can see that it only encloses the little charge Q, right? So this is our Q enclosed, and that means our electric field then is just given by a normal Gaussian surface with that as the enclosed charge. So Q over 4 pi epsilon naught R squared. Awesome. We can continue on here to part D, and now we want to figure out what the electric field is for R greater than R1, but less than R naught. So here we should know this is R1, R naught. That's our Gaussian surface here. This is all inside of the conductor. And inside of the conductor, by definition, we know the electric field is zero, because that's true for every conductor. Lastly, we go to part E, and this is for R greater than R naught. So we now can enclose or put a Gaussian surface just outside of R naught. And how much charge does this enclose? Well, that means the total enclosed will be the Q conductor plus the test charge. And we already said the conductor has a total charge of Q. So this is just Q plus Q. So now we can know that the electric field from Gauss's law looks like a point charge with charge Q enclosed. So Q enclosed over 4 pi epsilon naught R squared. And this is just big Q plus little q all over the same thing. And that is E. Awesome. That's it. You can see here that it's much easier to calculate these things as with the shell being a conductor than as if it's non-conducting. When you have to worry about the charges accumulated across the volume uniformly, it gets a